Okay, let's take a look at a situation that deals with forces happening at angles. And this is kind of a basic problem that we'll build on with a lot of different variations to it. This has a 100-kilogram crate sliding down a 38-degree ramp at a constant velocity. Okay? There's actually a lot of information in that one little statement. What we're going to try to do is analyze this and figure out the coefficient of friction between the ramp and the crate as it slides down. Okay. Now, I'm going to save that for the end. First thing I'm going to do is just set up how to analyze situations where you have forces happening at angles. Okay, so this is a very common one. So I'm going to draw something, and look, no matter whether this was a crate or a little person or a dog, I wouldn't care. I'm going to draw a box. Okay, I always draw a box. Number one, I can't draw, and number two, the box actually gives me some things, some space to put stuff on the inside, and it's kind of a systematic approach for me. If I have a big box there, I kind of know how to label everything when I get used to the process. So the first thing we got to recognize is this box, okay, this crate is being pulled towards the earth by gravity, okay? But it's not being pulled into the ramp, so to speak, it's being pulled straight down. So this is a case where gravity's pulling it straight down, but then I've got a ramp pushing it at a certain angle, and those two angles are not like exact opposites of each other. They're related, but they're not, it's not like one is going one direction and one's exactly the opposite of the other. So in this case, we're going to have to analyze some angles. Now I'm going to draw the weight as a vector going down, straight down. Let's see if I can do this without making it look too terrible. Okay. So I'm drawing the weight as a vector inside the box going straight down. There's many ways to do this, and this isn't the way I learned, but this is the way that I've kind of morphed into over time because it just is easier to represent things in my opinion. So this is the weight, this is the force of weight, and remember the force of weight, we calculate that by m times g, mass times the acceleration due to gravity. So I'm going to label that mg. Now this has some components to it. I've got a component right here, and I've got a component right there. And it makes a 90-degree angle. This is a right triangle. And if you go back to your geometry knowledge, this triangle is congruent to this triangle. Basically, if I took this triangle and I flipped it upside down and then rotated it, I would have this one right there. So this 38-degree angle represents that 38-degree angle. Okay, so those two triangles are the same. One's just a smaller version of the other, but the angles are identical. And we're going to use this as a way to calculate components of the weight. Okay, because when I set a box on this ramp, part of the weight is pulling it down the ramp, and part of the weight is pulling it into the ramp. And I need to split those into pieces. Just like with projectiles, we had our horizontal component and our vertical component. Here we have a component that goes downhill and a component that goes into the hill, so to speak. So I'm going to figure out the formula for those. And if I use my trig right, this one here is going to be mg times the cosine of theta, because it's the red one is the adjacent side to that angle. And then the blue one is mg sine of theta. And what I'd like to do before I actually get into analysis of the forces that are all happening is I want to split up and get those two components, just like we did with velocities and projectiles. Because once I get these two components, I'm pretty much going to ignore the overall weight, because in this case it doesn't really apply. Some of the weight's going downhill and some of it's going into the hill. So let's type that into a calculator and get that. Okay, so in this case, I got it written down here because I did it ahead of time. mg is just going to be, we said 100 kilograms times 9.8. Oops, I got to use my black pen here. mg is going to be 980 newtons. Okay. But I want to know the red and the blue components here. The blue component, so 980 times sine of 38 gives me 603 newtons. 603.3 newtons. Okay. So there's the component that is represented by the blue line up here. The one that's the red line is 980 times the cosine of 38, which ends up being 772.2. So I went ahead and split that up into its trig components before I get started. And now I want to interpret what's happening. So what I usually do is I draw all those forces of gravity, all the gravitational components I put inside the box. On the outside of the box for my free body diagram, I'm going to put all the specific forces that apply to this situation. Okay? So for example, and I don't have a great way of saying this, but I can tell you what students have done in the past. We look at this and we go, hey, some of the weight is pulling this down the hill. This is obviously going down the hill at a constant velocity. Okay, so it's traveling down the hill. So there's got to be a force that's pulling it down. It happens to be equivalent to this one that you look at, and it looks like it's going parallel to that ramp. That is a vector that represents the force that's taking this downhill. So I'm going to draw this out here. This is force, and we're going to label it something. In this case, I'm just going to keep it consistent. I'm going to put a DH here for downhill. Now, there's a lot of ways you could name this. You can call it an applied force. You can call it a gravitational force. I'm not going to try to confuse you. I'm saying this is the force that's going downhill, and it's represented by the blue vector up here that's parallel to the downhill direction. Now, I've also got the ramp pushing this direction. Okay, we call that the normal force. It's perpendicular to the surface that's being contacted. And that is this red component. This red component shows me how strongly with what force is that ramp pushing against the crate. Okay, that is my normal force. It used to go straight up and down in our normal flat situations, but this is angled, so it's going to be pushing out. But you can see red is pushing this way. That is the normal force. Okay, my normal force is going to be this cosine component. This is 772.2 newtons. I got one other thing happening here, and that is friction. Okay, I got friction, and remember, friction always opposes motion. If this is sliding down the ramp, then friction is holding it back and not allowing it to do it as well. So I have a force of friction going against the motion. Okay, and I'm going to try to calculate that. Okay, or I'm going to try to reason my way through. Now I'm going to take a look at what the question's asking me. The question is asking me not for the force of friction, but the coefficient of friction. So I'm going to write down mu equals force of friction divided by the normal force. This is the definition of the coefficient of friction. Okay. The problem is I need the frictional force in order to calculate the coefficient. I got to have that somewhere. But the nice part is Newton's second law tells us what this should be. So here's where you have to sort of build each situation on its own, and you can't just use a formula you had in a previous situation because every situation is a little different. So there are two things we can do here with Newton's law. Newton's law said the net force equals mass times acceleration. And we also can figure out the net force by looking at, by looking at the diagram and figuring out what is happening. We have to build an equation that tells us, here's the total of all the forces this is feeling. Okay. So I'm going to start right here. Net force is equal to mass times acceleration. Do we know anything about that? We do. This is huge. These two words here in the problem give us a big hint. This thing is sliding down a ramp at a constant velocity. So it's moving, yes, but it's not speeding up and it's not slowing down. And what that means is if the acceleration is zero, constant velocity means there's no acceleration. It means the acceleration is zero, then my net force is equal to zero. Okay, that's a big deal. In real life, what that means is the part of gravity that's pulling this down, the downhill force that's pulling it this way, has got to be getting balanced out or canceled out by the friction that's holding it back. These two forces are essentially equal to each other. They're just in opposite directions. Because, think about it, if this force down here, this downhill force was bigger than the friction that's holding it back, then this box should be speeding up as it goes down the ramp. It should be accelerating. If this force here is a lot smaller than friction, then the box isn't going to move at all. It's not enough to actually have it move. So we have that equilibrium in the middle where it's moving at a constant speed. So that means this force pulling it down must be getting canceled out by the friction holding it back, and essentially it's just coasting. It's not speeding up and it's not slowing down. So let's take a look at how we would do that mathematically. First thing I want you to recognize is this downhill force is the same as that component. I didn't write it in, but I should have. 603.3 newtons. Okay. So what I'm going to do is I'm going to build an equation for net force based on what I see here. And the forces that are affecting it in this direction, the direction that it's moving, I'm going to try to somehow make sense of those. This situation is different from a lot of other ones, but I'm just going to describe this situation. What I'm going to say is that the net force is going to be equal to the downhill force minus the frictional force. Now, there's lots of ways you could write that. Most people would write the downhill force plus the frictional force, and then make the frictional force a negative value. I'm going to deal with it in absolute values. This force downhill, if I subtract the force that's holding it back, that should tell me the overall extra force that this is feeling. And we know the overall extra force that this is feeling, the total effect, is 0. So 0 equals the downhill force minus the frictional force. And what that means in reality when I try to rearrange this is it means I can move this over here and say that the frictional force is equal to the downhill force. Is that true always? No. It's true in this problem. This is what makes physics so difficult is you have all kinds of stuff to work with, but when you get right to here, you have to take and build an equation that represents this situation only. And that situation will be different every time. So we have to look at it and say, this minus this is going to give me my total, and my total happens to be 0 because of the constant velocity. It won't always be that way. What it does for me here is makes my calculations actually not too bad. I got a lot of stuff labeled up here, but this really means that I have 603.3 newtons pulling it back, or pulling it down, and I have 603.3 newtons holding it back. That is my frictional force. How do I calculate mu? Well, I take the frictional force divided by the normal force, that surface that's pushing up on it. So to get mu, I'm going to take my friction, which I figured out with Newton's second law. My friction is 603.3. And my normal force is 772.2. And I'm going to divide those, and it's going to give me a ratio, like a percentage, that describes the effect of friction in this case. 603.3 divided by 772.2. And I get 0.78. So the coefficient of friction in this case is 0.78. Now, it doesn't seem like there's a ton of math there. It all depends, but this is the spot. This is where everybody tends to get stuck in physics because it's not just plugging in a formula, it's building a formula to represent this situation. So this is kind of where we have to go. You have to use Newton's second law and see if there is a net force. Like, was there an acceleration here we could use? And then you have to figure out what forces build up the net force. What's the ones that are having an overall effect on the direction of motion? And then we make a formula to fit that, and then we do a little bit of math. Okay. So it's going to take some getting used to. We'll do several of these problems where they have different parameters, and you can see how you adjust for those.